And we are starting to record. All right. Today, we are jumping into a new topic, a very brand new topic. It'll be a nice change of pace from our more classical math-based topics we've spent time on over the last few weeks. But of course, recognize with that, we are officially starting module exam 4 content. And our very first topic is drawing. Specifically, we'll be drawing Lewis structures and VSEPR geometries. Now, as the term suggests, we will be spending a lot of time actually drawing stuff out. But I want to spend some time on explaining so we can understand what a Lewis structure is, and of course, what that term VSEPR stands for. Now, to start things off, Lewis structures are the first step to determining a compound's three-dimensional geometry. Lewis structures are the first step to identifying a compound's three-dimensional geometry. When we say 3D, of course, recognize up until this point in the class, we've frequently just written stuff on paper. When we, for example, written out chemical compounds like HCl or CaCO3, we don't pay too much attention to what the geometry is. We don't really know if something's on top, on the bottom, left, right, front, back, or whatever. We just see them in two-dimensional, just written out. Now, the thing about Lewis structures, or rather what they do to help us identify 3D geometry, is that Lewis structures, here just abbreviated as LS, Lewis structures explicitly show the nature and location of all valence electrons. Now, there's a term we haven't heard from in a while, valence. We talked about it way back when we were doing module 1 content vis-a-vis naming, charges, all that nice stuff. So let's just remind ourselves of what that term valence means. It quite literally means outermost. We've talked about how atoms, like a planet, has rings around the nucleus, and it's these rings where the electrons can be found. The outermost ring are where the outermost electrons can be found. We've, of course, seen this before. Valence electrons has a direct correlation to an element's group number. So to remind ourselves, let's go through all of the groups and how much valence electrons we expect to find. We have groups 1, 2, 3 to 12, 13, 14, 15, 16, 17, and 18. Now we're going to look at the number of valence electrons present. Group 1 has 1 valence electron. Let me put some lines between these so it's easier to see the separation. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Groups 3 to 12, if we remember, are actually those transition metals. So they have a variable number of valence electrons. Remember, that's what gives rise to us not knowing for sure how many electrons or what the charge is of a transition metal is. Group 13 has 3 valence electrons, 14 is 4, 15 is 5, 6, 7, 8. So in theory, the concept of valence electrons should not be something new to you. It's something we've talked about at length over the course of the semester. Now, while we're on this topic, just a quick reminder, hydrogen is in group 1. Let's just make something absolutely clear. Hydrogen will always contribute 1 electron. Don't forget also the thing about hydrogen is that it's fine with 2 electrons, aka the octet rule. Remember, we talked about how the octet rule is really what describes or explains the popularity of the group 18, the noble gases. That octet rule basically states that atoms love to have 8 electrons in its valence shell because that's what royalty has. Hydrogen is closest to helium. Helium actually only has 2 electrons. It is still considered noble gas. It's still in group 18. So this is the one atom that doesn't follow the octet rule numerically. Helium has only 2 electrons. So in the case of hydrogen, we're fine with just 2. Everyone should have a copy of a single, it's a portrait, it's a procedure-based document. Let me see if I can grab the document myself on mine. I'll put it up. Oops. 1A. Notes. This document, now that I have it up on the TV, is the written procedure step by step to help us draw the Lewis structure of a molecule. It also has a couple additional pages attached to it. On the second page, it shows you how to go from Lewis structure to VSEPR. That's something we'll talk about in probably like 10 to 15 minutes. And then it gives you a chart at the end. Over the course of this lecture, we'll understand a little bit more about what these different pieces are. But for right now, I want us all to focus on the very first page. These are our step-by-step instructions to drawing the Lewis structure of a molecule. You will not be given this procedure as part of your exam booklet. You are expected to memorize it. In other words, all I will say on the exam is draw the Lewis structure. Draw the Lewis structure, and that's it. Now, I'd like to go over a couple of random questions, sample questions that illustrate how to draw Lewis structures from these steps. As wordy as this is, I know immediately we're thinking, oh my God, this is a lot to memorize. It's not as detailed as it makes it seem. In fact, over the course of time, you might realize this takes less than 5 minutes. So with that in hand, let's first draw the Lewis structure for water. Okay. As we can see, let me just get a hard copy myself so I don't need to keep going back. It reads, to determine the Lewis structure of a molecule, the very first thing we need to do is calculate the total number of valence electrons for the molecule. What does that mean? It means you're going to use each element's group number as the valence electrons. For example, group 17, this should be 17, sorry, contributes 7 valence electrons. Cations, you must subtract electrons equal to the charge. Anions, you must add equal to the charge. So let's do that first for water. So we're going to first determine the total number of valence electrons, here represented as VE. We know that in water, there are 2 hydrogen atoms and there is 1 oxygen atom. We know that hydrogen contributes 1 electron. And we know that oxygen in group 16 contributes 6 electrons. This gives us a total of 8 valence electrons. Now, Lewis structures in detail, in short, they do show us where all of these 8 valence electrons I'm so sorry about that, are. We need to know the nature of these electrons and where they're located. And when I say nature, I mean, are they in a bond or are they a lone pair? Recognize that the molecule as written is not a cation, nor is it an anion. So we can skip straight to step 2. Step 2 reads, assume a central atom and arrange other atoms around it. Now, that word there at the very beginning, it says assume a central atom. In truth, there is no 100% foolproof method to be able to very easily identify what the central atom is. Every single time you draw a Lewis structure, you are making, at best, an educated guess. That means you have to accept the possibility that your assumption may be wrong and you may need to start the process over. But to begin, you have to assume a central atom. Now, the thing about assuming a central atom is that logic and intuition does play a role. See, for example, here we have H2O. There are a couple different ways that these 3 atoms can rearrange themselves. For example, we can have 2 hydrogens first and then an oxygen. We can have an oxygen, then 2 hydrogens. Or we can have a hydrogen, an oxygen, and then another hydrogen. Please notice that although these are all the same atoms, they're in different orders. Of course, the 2 hydrogens are identical, but otherwise, what's different? In this case, a central atom is a hydrogen. In this case, a central atom is a hydrogen. And in the last one, the central atom is an oxygen. And I do literally mean central atom, the atom in the center. Now, logically, we should be able to intuit that the structure that makes the most sense is this bottom one right here. In other words, oxygen immediately in the center with 2 hydrogens on opposite sides, because this is the most unbiased version. In other words, if you had picked one of these on top, how would you know that this hydrogen is in the center versus that hydrogen? The fact that that question cannot be easily answered is what tells you these on top are wrong. In other words, we're able to very quickly and easily assume that there is an oxygen in the center and there are 2 hydrogens that surround it. Now, I've drawn this landscape just as though you're writing it on lined paper. Arranging it can take whichever form. You could have, for example, put the hydrogens on top or on the bottom, or you could have put it diagonally. All that matters here is that there is a clearly defined central atom and all other atoms are arranged around it. It says, connect each outside atom to the central atom with single bonds. All right, so we have our outside atoms, we have our hydrogens. We're going to connect them to our central atom using just single bonds. Now, don't forget that these single bonds are comprised of 2 electrons. A single bond is 2 electrons, a double bond is 4 electrons, a triple bond is 6, and so forth. So in drawing this assumed structure, we have actually already explained 1, 2, 3, 4 electrons. So we started with 8, now we have 4 left to explain. Remember, Lewis structures explicitly show the location and nature of all valence electrons. We can see just by drawing the bonds that 4 valence electrons actually exist in bonds between each outside atom and the central atom, oxygen. Step 3, distribute electrons working from the outside in. We are going to allocate the remaining valence electrons to satisfy each atom's octet requirement. Remember that the octet requirement can be 8 and sometimes 2 if it's close to hydrogen, where again, we're ultimately trying to get as close to noble gases as possible. You will then assign any leftover electrons to the central atom as lone pairs. So that's where that outside in comes from. You're going to satisfy the outside atoms first, and with whatever electrons you have left, you're going to assign them to the central atom. I see a hand, Sarah.
Does that mean that we only put one electron on the hydrogen, or are there still two?
We're about to get to that right now. So focus on the central atoms first, just starting over here on the left. If we zoom in, we can see that this hydrogen has access to 1, 2 electrons. Hydrogen, being close to helium, tells us that it is satisfied with 2 valence electrons. So this hydrogen, as written, is satisfied. You can apply the exact same logic to the hydrogen on the right, where again, it currently has access to 2 electrons, aka octet. So the outside atoms are now happy. We will then assign any leftover electrons, the 4, to the central atom. How we do that is we quite literally pair them up and just place them on the central atom. This simple drawing clearly shows us all 8 valence electrons. Although will not always be explicitly drawn those dots, we do know there is a single bond between each atom. 1, 2, 3, 4, 5, 6, 7, 8. As of right now, this molecule, as drawn, shows all 8 valence electrons. Number 4, check happiness. Each bond or lone pair should be very clearly indicated. Check. Ensure all atoms have complete octets. Hydrogen has 2, hydrogen has 2, so they're checked off. Let's look at the oxygen. As drawn, the oxygen has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. This oxygen is also satisfied. With that, every single atom here has a full octet. If any outside atom lacks a full octet, start over, doesn't apply here. If the central atom lacks a full octet, doesn't apply here. Convert the lone, well, we don't need to continue to step 5. Finally, we're going to go to step 7, which is to calculate and clearly indicate the formal charge of each atom. This is a brand new term, formal charge. The formal charge of an atom is its individual charge within a molecule. It is not equal to the atom's ideal charge, meaning you cannot just know the formal charge of an atom, you have to calculate it. The formula is given here. Formal charge is equal to the group number minus the number of lone pairs times 2 minus the number of bonds. Whoops. We are going to calculate the formal charge of each atom in this molecule using that formula. Arbitrarily starting with hydrogen on the left, we go in order. Hydrogen is in group 1 minus the number of lone pairs. Well, the hydrogen has no lone pairs. 0 times 2 is 0. Minus the number of bonds. We can see that that hydrogen specifically has 1 bond. That's equal to 0. So the formal charge of this hydrogen is 0, aka neutral. If we apply the same logic to the hydrogen on the right, to no one's surprise, it's almost the exact same set of numbers. Hydrogen is in group 1. The hydrogen has 0 lone pairs, and the hydrogen has 1 bond. The formal charge here is also 0. That gives us something important to recognize. These two hydrogens are identical. So once you calculated one set of formal charge, you didn't need to do it for the other because they'd be the same. Now let's calculate the formal charge for the oxygen. Oxygen, this is the tough part now. Oxygen is in group 16. However, when thinking about group number, we specifically talk about their valence number of electrons. So oxygen may be in group 16, but it has 6 valence electrons. We see that it currently has 2 lone pairs. Remember that word, lone pairs. They're pairs of electrons. We see that there are 2 pairs, 2 sets. This will be 2 times 2 minus the number of bonds. The oxygen in the middle has in total 2 bonds. This gives us 6 minus 4 minus 2. Simple math should be able to tell us this is immediately 0. So in this case, we see that the formal charge of every single atom here is 0, aka neutral. This is not particularly satisfying or dissatisfying to note. It's just the way the math worked out. It simply confirms to us that each atom has an individual charge of 0. Once you do that, you are done. This right here, that HOH, is the Lewis structure of water. The Lewis structure shows very clearly all of the valence electrons, where they're located, and their nature. Upon drawing a Lewis structure, we can then determine the compound's VSEPR geometry. I would now like for us to turn to the second page of the handout. VSEPR stands for valence shell electron pair repulsion. Now, you maybe notice how I've been pronouncing it. I've been pronouncing it VSEPR as in VESPR. It is, of course, spelled VSEPR. Ultimately, the pronunciation is very clearly understood when we refer to VSEPR, even if it's not spelled the way we sound, we know what we're talking about. So I will continually refer to this as VSEPR. VSEPR theory offers a systematic approach to predicting the 3-dimensional arrangement of atoms in a molecule. You see, remember, all of this has been about trying to determine the compound's 3-dimensional geometry. The first thing we had to do was determine the Lewis structure. As I said, it explicitly identifies the nature and location of valence electrons. To determine the VSEPR geometry of any molecule, you simply need to follow these 2 steps. Number 1, propose a Lewis structure of the molecule as normal. We just did that for water. Then we will do what's called referencing the VSEPR chart. Here's how that works. Once you have your Lewis structure, in this case, water, HOH, you will identify the number of atoms bonded to the central atom, as well as the number of lone pairs on the central atom. Taking a note right here, we see there are 2 atoms attached to the central, and there are 2 lone pairs attached to the central. Once you identify that, you will identify and find the matching geometry. This leads us to the VSEPR chart shown here. The VSEPR chart shows generic structures of varied types and various numbers that overall allow us to predict the shape of a molecule. We are looking for a generic template that has 2 atoms attached to the central atom, as well as 2 lone pairs. As we scan through the list, we should notice this one right here. This generic drawing has a central atom that has 2 atoms connected to it and 2 lone pairs. No other template here follows that exact criteria. In other words, if we were to look at one immediately to the left, what we would see instead is that central atom attached to 3 atoms and attached to 1 lone pair. That is what tells us that our VSEPR geometry will most closely resemble the bent or angular VSEPR geometry. Upon identifying the geometry, you simply need to redraw the structure matching that template. Be sure to include any bond angles in your final answer. So all we're going to do is, starting from this generic shape right here, we're going to try to match that template. We know our oxygen atom is in the center, and we can see that the 2 atoms are no longer linear, but rather slightly bent at an angle. Similarly, we see that the lone pairs are on a different type of bond. It looks a little strange. We have here on one side a wedge, and we have on the other side a dash. All you need to know about these new bonds, the dash or the wedge, is that the dash represents some things in the back, and the wedge represents some things in the front. So what I'm trying to say, and I'm going to come up so you can visualize it, is that if you were to pretend that my chest is the oxygen atom in the center, the hydrogens are at some bent angle to that central atom, my hands. The lone pairs, one is in front of me, one of them is behind me. Of course, if you're looking at me head on, you wouldn't see the one in the back, but you know it's there. And that's the significance of the wedge and the dash. They represent that you're no longer in line with the paper, with the plane, but you're either pointing out or pointing back. You do not need to be able to identify whether something is in the front or the back because, well, the VSEPR chart gives it to you. In some cases, it defines atoms as being on the wedge or the dash. And in some cases, it defines the lone pair as being the wedge or the dash. This is all to say that when referring to the VSEPR chart, you simply need to match it to the best of your ability. All that's left is to include the bond angle, which we see here between the 2 atoms is less than 109 degrees. Yes, Sarah. I'm getting to it. Now, I'd like to point something out. Notice that there are two less than symbols here. That is on purpose. The multiple less than symbols just tell us it's much, much lesser than. For example, if I said less than 109, that could be somewhere like 107 degrees. If it's much, much less than 109, that's something closer to like 103 degrees. The point is that the number of less than symbols that signify the magnitude. The name of this geometry is known as bent, or sometimes referred to as angular. With this, we now see the three-dimensional geometry of the molecule. We can see that oxygen, which is our central atom, has two hydrogen atoms in the same plane, approximately 109 degrees apart, very, very less than 109 specifically. And it has two lone pairs, one in the front, one in the back. Now, it's important to know that the VSEPR chart is simply a prediction. It allows us to, at the very minimum, assume what the estimated geometry is of a molecule. You would still need experimental evidence, such as growing crystals, looking under a microscope, to confirm or verify the particular angle. Oxygen or water, for example, has a known angle of approximately 104.5 degrees. You would not know that, but you do know that water is predicted to have a bond angle of very less than 109 degrees. And that, in essence, is the beauty and benefit of the VSEPR chart. It is used as a template to make a prediction, an educated prediction about the three-dimensional structure of a molecule. You do not need to memorize this chart, as this chart will be given to you on the exam. But you do need to memorize the steps. I will not provide you with the written steps on the exam, but I will provide you with the chart itself. If we go back to where we're writing over here, we now know the VSEPR geometry looks something like this. And it is described as bent. You could also use bent or the word angular. They mean the same thing. Recognize that, between the two, the VSEPR geometry identification, that's the easy part. Once you've identified how many atoms and lone pairs you have, then that's just matching it to the chart and redrawing it. But if you have an incorrect Lewis structure, well, then unfortunately, your VSEPR geometry is also going to be incorrect. Do we have any questions on water? All right. Let's keep going. Let's try another molecule. We're going to specifically work with H3O plus. First thing we're going to do, we have our steps on the sheet in front of us. We're going to follow the steps. The very first thing to do is determine the total number of valence electrons. We see there are 3 hydrogens and 1 oxygen. Each hydrogen contributes 3 electrons. Oxygen contributes 6 for a total of 9. However, you should notice immediately that there is a positive charge on the molecule. I've explicitly told you that it's positively charged. And as noted in the steps, for cations, subtract electrons equal to the charge. So we have +1 charge, a +1. That's what tells us we will subtract 1 from the total number for 8 valence electrons in full. Next step, we are going to assume a central atom and surround it with our outside atoms. We've done this for water, so it should be no problem for us to say that there are hydrogens that surround the oxygen. Notice I've kind of drawn it just arbitrarily. I put that third hydrogen on the bottom. If you wanted, you could have put it up on the top. A Lewis structure is your guess at the structure initially. It's the VSEPR that really tells you where everything is, top, bottom, left, right, wedge, dash. So when you're drawing your Lewis structure, your initial drawing doesn't have to be the perfect geometry. You're just drawing something out. Connect each outside atom to the central atom with single bonds. 3 single bonds means that we have currently explained 1, 2, 3, 4, 5, 6 electrons. So we're left with 2 to explain. Now we're going to distribute electrons working from the outside in. Each of these hydrogens, as written, has access to 2 electrons. That's fine. That satisfied octet. So no more lone pairs on the hydrogen. All that's left is our central atom oxygen, and we allocate those remaining electrons to the central as a lone pair. Now, it's very important that you do draw the pair as a pair, meaning don't draw the electrons far apart like that. That just doesn't look right. Please pair them up together. And I've been told I have a slight accent, of course, when I'm saying the word pair as in P-A-I-R. I sometimes pronounce bear like beer. The animal versus the drink. Okay. Now that we've assigned electrons, we're going to check happiness. Each of these hydrogens have 2 electrons. They're happy. Done. The oxygen in the center has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. The oxygen is happy. Everything is happy, so now we calculate formal charge. Starting with the hydrogens first, recognize that each hydrogen is identical to one another. So by calculating 1, you calculate them all. Hydrogen, 1 valence electron, 0 lone pairs, 1 bond. This is a whopping 0. Now we calculate the formal charge of the oxygen. Don't forget, by calculating 1 hydrogen, since all the others are identical, we've calculated them all. So we don't need to spend time on each individual calculation. Now on to the oxygen. Oxygen has 6 valence electrons. We see that it has 1 lone pair. And we see that it has 3 bonds. This is equal to 6 minus 2 minus 3. Some simple numbers in front of us. 6 minus 2 is 4. 4 minus 3 is plus 1. This is what tells us that oxygen specifically has a positive charge on the atom. And right here is the beauty or benefit of calculating formal charge. You see, I gave you H3O+. As written, H3O plus, as written, there is no way you could have known with absolute certainty that the positive charge was going to be on the oxygen specifically. That's why we calculate formal charge. Formal charge allows us to identify which atoms carry which specific charge. In doing so, we have now explained all 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. We have also explained where this positive charge comes from. This right here is our Lewis structure for H3O plus. I'm just going to write Lewis S for short. Guess what we're going to do now? Now we're going to determine the VSEPR geometry of this molecule. First thing to do is identify how many atoms and lone pairs are on the central atom. This has 3 atoms attached and 1 lone pair, here abbreviated as LP. Take a stab for yourself, look at the chart. Don't shout out the answer, but see if you can identify which template this is. We're looking for a central atom with 3 atoms attached and 1 lone pair. Evaluate each template to see if it matches. Hopefully, we've all come to the same conclusion. Trigonal pyramid. It is the only template that has a central atom connected to 3 atoms and 1 lone pair. So we're going to take this template over and we're going to draw the H3O plus. We have oxygen in the center. We have our wedge, our dash, and our bond. Each of those are connected to atoms, so they're all hydrogens. And then on top, we have our lone pair. We can see from the template that the bond angle is less than 109. And of course, from the template, we know specifically this is trigonal pyramid. Yet again, it was not up to us to decide specifically what's on wedge, dash, or line. The template tells us exactly. So as long as you've identified the VSEPR correctly, it's just a matter of matching it. Don't forget that we do need to include that positive charge on the oxygen. Do we have any questions about H3O plus? Yes, Catherine.
Why did you subtract 2 from the valence electron?
Where?
The red.
Oh, those are the lone pairs. Right? Remember that 6 of them came from the bonds. So we had 2 left. And those 2 went on to the oxygen as a lone pair. So we've explained all 8 electrons. Good? Nick, what's your question?
And using it as a XY with like the number of electron pairs and the lone pairs. It would lead you to believe that it's state of things are angular, but the drawing here, the lone pair is actually like it has 8 pairs, so it would be 4, right? If you're looking at the chart.
4 things. So
Pairs
correct. Yes. Correct.
Okay.
Yeah. So I'd like to just point one thing out here when it comes to VSEPR geometry. When I think about VSEPR geometry, I think about, for lack of a better analogy, having roommates. That is, within the same room, we each have our own bed. Every person wants their own personal space, but certain things take up more space than others. Those electrons on top are so pushy, they're gonna be like, I'm gonna shove you guys to the bottom bunk. I don't care what happens because I wanna be on the top bunk. And that's where the angles come from. You see, in an ideal world, everyone gets their own space, everyone gets shared equally, but this has lone pairs, and the lone pairs reign supreme, and it says, no, I need my personal space, and I don't care what you guys have to say. I'm pushing you out of the way. All right? Let's try another one. Yes, Prof, sorry.
There the oxygen positive, it's become negative. If the oxygen wasn't negative, it become positive.
That's a good question. We're about to do an example just like that right now. So hopefully that will answer your question. Let us now try an ion that you all should recognize. NO3 minus, a polyatomic ion, nitrate. Before we begin, does anyone want to take a guess on which atom that negative charge resides? Probably the N, is that what you said? Yeah, okay. So we have one guess saying that the nitrogen is where that negative charge is going to lie. Let's see if that's true. First and foremost, we're going to calculate valence electrons. We're going to sum them up. We have 1 nitrogen added to 3 oxygens. Nitrogen in group 15 has 5 electrons. Oxygen, we've seen it a couple of times, is in group 16 for a total of 6 valence electrons. This is 5 plus 18 for a total of 23. Recognize we're dealing with an anion, a negative charge. According to our steps, for anions, you add electrons. So 23 plus 1 is equal to 24. So we have 24 valence electrons to explain when drawing the Lewis structure for NO3. First thing we're going to do is we're going to assume a central atom. We've seen 2 examples right now. Anyone want to take a guess or assume what the central atom is here? The N. It makes the most sense. There are 3 oxygens. So it makes the most sense that there is a nitrogen in the center with 3 oxygens around it. We are then going to connect each outside atom to the central with single bonds. With that, we've explained 6 valence electrons. We have 18 left. Now we are going to distribute our remaining electrons working from the outside in. Starting with the oxygens. Oxygen, right now, currently has access to 2 electrons. Now, oxygen is not close to helium. It's close to the other noble gas, so we're actually looking for a total of 8. So we're going to add 1, 2, 3, 4, 5, 6 electrons. By adding these 3 lone pairs, this oxygen now in total has 8 valence electrons. We can apply that exact logic to all of the oxygen atoms. Two, 4, 6, 8, 10, 12, 14, 16, 18. We have now explained the remaining 18 electrons. I see a hand, Naomi. Meaning right here? No, that would be confusing because then all of a sudden you're saying, are these the electrons in the bond or are they in addition to? So that ambiguity is why we would not do it. Writing it out this way makes it clear there is a couple electrons right here and there are 3 lone pairs. Okay, now step 4, we're going to check happiness. Each of these oxygens currently has access to 8 electrons. Confirm for yourselves. So each of these oxygens on the outside are happy. Let's look at the nitrogen. As of right now, the nitrogen has access to 1, 2, 3, 4, 5, 6 electrons. That's not happy. That's not happy at all. We're looking for an octet. If any outside atom lacks a full octet, start over. Clearly, that doesn't apply here. If only the central atom lacks a full octet, consider the possibility of multiple bonds. Continue to step 5. Step 5 says, convert the lone pairs on outside atoms to bonds to the central atom. By converting one lone pair, we will form a double bond. If we convert it 2, then that will form a triple bond. So here's what that looks like. This nitrogen right here currently has 6 valence electrons. That's unhappy. All it needs is 2 more. So it goes to its roommate and says, hey man, can I borrow some electrons? Does it matter which oxygen we borrow from? No, they're all identical at this point, so it doesn't matter which one we borrow from. I'm arbitrarily going to pick the one on top. I'm going to say that this lone pair over here on the right gets converted into a double bond. Now, let's be clear about something here with the conversion. Converting the lone pair to a double bond does not strip the atom of its electrons. In fact, this oxygen still has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. It still is happy. We've just converted how the lone pair looks. Now, this nitrogen has access to 1, 2, 3, 4, 5, 6, 7, 8. The nitrogen, as well as all other atoms, are now happy. Check happiness again. We just did that. Now we're going to calculate formal charge. Let me get that equation up here so we can just refer to it. Let's start with the oxygen on the left. I've used my subscripts FC, formal charge, O for oxygen, L for left. The formal charge of the oxygen on the left, it has 6 valence electrons, 3 lone pairs, and 1 bond. This is 6 minus 1 for a total of -1. That's what tells us the oxygen on the left has the negative charge. How about the oxygen on the right? Do I need to spend time manually calculating this? No, I don't. Recognize that both of these oxygens are identical. So I don't even need to spend time. I can quickly say -1. So this oxygen over here is also -1. Can I make that exact assumption for the oxygen on top? No. Visually, it's immediately clear this is not at all identical to the others. So we need to purposefully calculate that. The formal charge of the oxygen on top, 6 valence electrons, 2 lone pairs, 2 bonds. 6 minus 4 minus 2 gives us 0. So the oxygen on top with the double bond has a formal charge of 0. All that's left, of course, is the nitrogen. Nitrogen in group 15 has 5 valence electrons. It has 0 lone pairs, and in total has 4 bonds. This is a whopping total of +1. Looking at the structure, looking at the charges, does this explain why NO3 is -1 overall? Yeah. Why? Because the positive and the minus, one of them will cancel each other out, and all you're left with is a negative. Earlier, I had asked, take a guess where you think the negative is going to be. At the time, we guessed that it was going to be on the nitrogen. It was just a guess. We can clearly see now that was incorrect. And the only way we could have known that is by actually calculating formal charge. And herein lies the power of formal charge calculations. We see from the NO3 that the molecule is -1 overall. But individual atoms have their own set of charges. As long as it overall equals a negative, then we're good. That's NO3. Let's draw the Lewis structure, and then we're going to get the VSEPR. This is the Lewis structure. Now we're going to get the VSEPR. What are we looking for? We're looking for a central atom that has 3 atoms attached to it. Are there any lone pairs? No. Take a scan through the chart for yourself. See if you can find it. We're looking for a central atom connected to 3 atoms. No lone pairs. The answer we should all arrive at is trigonal planar. From the VSEPR, nitrogen in the center, double bond, single bond, single bond, with a bond angle of approximately 120 degrees, officially called trigonal planar. Remember what I said about lone pairs and them being your roommates. They're the ones that want their personal space. They're the ones that are going to push you down. No lone pairs here. Everyone gets their own equal space. They're all 120 degrees apart. This is the ideal outcome. Something I would like you to note is that when converting it to the VSEPR, the fact that this is a double bond does not matter. Meaning, on the VSEPR chart, every bond you see here is a single bond. Remember, these are just templates. We're only looking at number of atoms and lone pairs. Let's do another one. Let's do OH minus, another polyatomic ion. Hopefully we're getting the hang of the steps by now. I don't expect to have it memorized yet, of course. First thing we're going to do is calculate valence electrons. 6 comes from the oxygen. 1 comes from the hydrogen. And don't forget, it is an anion. So 1 more. This is a total of 8 valence electrons. Now we're going to assume the central atom. Now think about that word central. When we say something is in the center, we say things surround it. If we assume the central atom is oxygen, all that's left is the hydrogen. Technically speaking, depending on your perspective, couldn't they both be the central atom? I mean, it's just 2 points. So when dealing with 2 atoms and only 2 atoms, there is no central atom because there's only 2 points. We connect the 2. In doing so, we've explained away 2 electrons. We're left with 6. Now we're going to assign lone pairs, satisfying the octet. From the perspective of the hydrogen, hydrogen has 2 valence electrons. It's fine, it's happy. From the perspective of the oxygen, it has 2 valence electrons, but it's closer to a neon. So it needs 8. So we're going to add 1, 2, 3, 4, 5, 6 electrons. That explains the remaining 6. Is oxygen now happy? Yeah. It has access to 1, 2, 3, 4, 5, 6, 7, 8. Now that each atom is happy, we're going to calculate the formal charge. Hydrogen, 1 valence electron, 0 lone pairs, and 1 bond for a total of 0. The formal charge of the oxygen, group 16, so 6 valence electrons, 3 lone pairs, and 1 bond. 6 minus 1 is equal to -1 overall, thus explaining where the negative charge is found. And now we're going to check the VSEPR charts. Can you find this on the VSEPR chart? No, you can't. Why? Because it's only 2 atoms. And whenever you only have 2 atoms, this is a straight line. This is linear. In other words, the Lewis structure we just drew is also the VSEPR geometry. No change because there's only 2 atoms. No bond angle either. Between 2 points is just a straight line. Do we have any questions on OH? Yes, Prob. So what we did here was there was a certain point, Prob, where we had this structure right here with the 2 dots, and we were checking happiness. Each of these oxygens are happy as written. This nitrogen only has 1, 2, 3, 4, 5, 6, not happy. So we picked a lone pair and added it to the bonds for a total of a double bond. In doing so, the nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8.
electron.
6. I mean, sorry, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right. Looking at today's in-class problem set, I want to mention a couple things. My promise to you, 2 promises. Number 1, you will never be asked to draw the Lewis structure or VSEPR of anything with a transition metal. That's on the footer of the procedure. Let me find it for you. P.S. You will never be asked to provide the electronic geometry of a molecule with a transition metal. Remember, transition metals are variable, so we don't know how many valence electrons it has. And here is my other promise to you. Due to the nature of this topic being, it's kind of like the alphabet, where as long as you understand the fundamentals, you can draw anything. But for the purposes of Chem 1A, having you draw anything is too much. My promise to you is this. Any drawing questions you get on your exam will be from this problem set. Meaning, if you attempt this problem set in full, you will have at least done any question I can throw at you. Throughout today, we've already done a couple of them. We've done H2O, we've done H3O plus, and we've done NO3 minus. So we've already done 3 of them. Your extra credits is any 5. Any 5 of these structures. And again, any question I give you about this topic will be from this packet. So there is 3, 7, 11, 15. There are 15 questions here. They will be from this packet. Do we have any questions? Okay. That's it for drawing. That's it for electronic geometry. We're going to end lecture for today. If you have any questions, come talk to me after class. If not, I'll see you guys in lab at 1:30. Yeah. Yes.
Add or should it negative?